Hello guys, my name is Pratyush and in this demo video, we are going to talk about the topic nanotechnology. As you very well know that this topic is very important in prelims as well as mains exam. A question always comes from this topic and it won't be a surprise if multiple questions come from this. So a very good understanding, a very good grasp of this topic is absolutely essential. So with that, let us start. Now, the term nanotechnology consists of two words, nano and technology. We have a general idea of what technology means. So let us start with what nano means or what is nano. If we talk about the term nano, then this term nano comes from ancient Greek and it means dwarf. So the word nano means dwarf or little or small. If we talk about its mathematical definition, then International System of Units defines 1 nano of something as 1 billionth or 10 to the power minus 9 of something. So 1 nano of a meter will be equal to 10 to the power minus 9 meter or 1 billionth of a meter. Similarly, 1 nanosecond will be equal to 10 to the power minus 9 seconds. If we try to understand how much small 1 nanometer is, we can use this illustration below. One glucose molecule is about 1 nanometers in size. Compare that to a virus. A virus is about 100 nanometers in size. A bacteria about 1000 nanometer per size. Whereas a tennis ball is about 100 million nanometer in size or about 10 centimeter in size. So we can say that one tennis ball is equivalent to 100 million molecules of glucose. That is how much small 1 nanometer can be or how much small 1 nanometer is. Now we know what nano is. We already knew what technology was. If we combine these two terms, we get the term nanotechnology. Let us try to understand what the term nanotechnology means. If we define nanotechnology, then nanotechnology is a field of research and innovation concerned with building some materials or devices on the scale of atoms and molecules. So whenever we are dealing with some materials or some devices, whenever we are manufacturing some materials or devices on atomic level or molecular level, on the size or on the scale of atoms and molecules, we are dealing with the field nanotechnology. Now, the reason we talk about this field, the reason we talk about nanotechnology is that it has numerous real life applications. Its real life applications are very, very numerous, or the potential for real life applications is very huge. In almost all major sectors, you can find some usage or some applications or potential for applications for nanotechnology, whether it be information technology, electronics, energy storage, medicine, biomedical field, national security, environmental science, aviations, solar cells, space sector, food security, agriculture. In almost all major sectors, nanotechnology can be used. That is why this particular topic becomes very important. Now let us talk about why nanotechnology, why we are talking about nanotechnology. So what we observed was that as we move from macro scale or from macro size, from meters, centimeters, millimeters to nanometers or nanoscale, what we observed was in those materials, there was a change in properties. That there was a change in physical properties, chemical properties, and biological properties. There was a change. Because of that change, new dimensions opened up or new avenues opened up for technology and applications. Because of this change, now we had new potential uses or new potential applications for those materials. Another reason is tech miniaturization. There is a need or there is a trend to manufacture, research even smaller and smaller devices, even smaller and smaller products. For example, we have an example here of Nokia Morph. It is a concept nanotechnology, how futuristic smartphones will look like. This is being researched by Nokia Research Center and Cambridge University in UK. This particular concept smartphone is flexible, stretchable, and transparent. It can be stretched, its screen can be stretched, or it can be bent according to the user's usage or convenience. So this is an example of how nanotechnology helps us in tech miniaturization and tech modernization. Another reason is scientific curiosity. Now, scientific curiosity is the urge to know more information, to know more scientific information, and it is an innate human trait. So, scientific curiosity is the third reason. Now, we said that as we go from macro scale to nanoscale, we observe the change in properties of materials. So, the logical question arises why there was a change in these properties. The first reason for that is electromagnetic force, role of electromagnetic force. What happens is at macro scale or in macro materials, the role of gravity dominates or the role of gravity predominates. Whereas as we move from macro scale to nanoscale, the role of electromagnetic force between particles starts dominating. Another reason is surface area to volume ratio. As we move towards nanoscale, the surface area to volume ratio of material starts increasing. With this increase in surface area to volume ratio, strength of the material also increases, whereas boiling and melting point decreases. Let us try to understand this with an illustration. Suppose we have this cube. It has a side of 8 centimeters. It has some surface area, some volume, and some surface area to volume ratio. As we start decreasing the side of this cube, its surface area to volume ratio starts increasing from 1 to 1.5 to 3. If we move towards, as we move towards nanoscale or towards nanometer, this particular ratio increases very much. It increases to a very high value. So the surface area to volume ratio starts increasing as the size of the material starts decreasing. The third reason is dual nature of light. As you know that light can behave as a particle as well as a wave. So as we go towards smaller values or towards nanoscale, the particle nature of light changes to wave nature. Light starts behaving as a wave. Now, because of all three reasons, at nanoscale, the principles of Newtonian mechanics cannot be used. We cannot use principles of classical mechanics. We cannot use Newton's 3 laws of motion. At nanoscale or at nano level, we have some new rules called rules of quantum mechanics. So we use them instead of rules of Newtonian mechanics. So these are the three reasons for changes. Electromagnetic force dominates over gravitational force. Surface area to volume ratio increases, and wave nature of light dominates. These are the three reasons why we observe a change in properties as we go towards or as we move towards nanoscale. Now we have talked about that there is a change in properties. We talked why there is a change in properties. The next question that comes to our minds is, what is this change? What is the change? Physical properties, chemical properties, biological properties, what is that change? So the first set of properties in which we discuss this change is optical properties, how the nanomaterial responds to light. In that we have some examples. The first example is gold. At macro scale, gold is yellow in color or golden in color, and it is mostly used in making jewelry. Whereas at nanoscale, gold is red, pink, black, or violet, and it is used in ceramic paintings. This is gold at macro scale. This is gold at nanoscale or nanoparticles of gold. It is red, pink, black, purple. It is used in ceramic paintings. Another example is zinc oxide. At macro scale, zinc oxide is white in color, whereas at nanoscale, zinc oxide is transparent. Both are used in sunscreen. You might have seen some cricketers while batting or while fielding, they have some white patches on their skin, on their noses, on their lips. That is because of zinc oxide. That is because of the kind of sunscreen that they use. So these white patches are because of sunscreen. In those sunscreen, zinc oxide must be in macro size. If you go out to the market and buy some good quality sunscreen, you apply it on your skin, you will find that that sunscreen is transparent or almost transparent. That is because the zinc oxide being used in the manufacturing of that sunscreen uses nanoparticles of zinc oxide. Now we talk about chemical properties of materials, or how the chemical reactivity increases manifold on transformation at nanoscale. If a material goes towards nano transformation, its chemical reactivity increases many times. One example is aluminium. At macro scale, aluminium is very stable. It is used in making utensils. Whereas at nanoscale, aluminium nanomaterials are highly explosive. They're used in making missiles, bombs, explosives, IEDs. So aluminium becomes very reactive at nanoscale. Another example is silver. At macro scale, silver is very stable. It is used in making utensils. It is used in making jewelry. Whereas at nanoscale, silver is very reactive. It is used as a sterilizing agent. You might have seen that Lifebuoy ad, where in the ad it says that the soap has silver ions, which helps kill germs. That is the property of silver as a sterilizing agent. So silver is used as a sterilizing agent at nano level or at nanoscale. The third set of properties that we discuss is electrical properties. So conductivity of a metal, it is observed that conductivity of a metal decreases with size. And the last set of properties is physical properties. We have already discussed that as we go towards nano transformation, surface area to volume ratio increases. Because of this increase, strength also increases, and melting point and boiling point decreases. So these are the physical properties. For example, copper and gold, they turn from soft to extremely hard on nano conversion. Compared to their macro materials of copper and gold, their nano materials are extremely hard. That is because their strength increases on nano transformation. Let us now understand in brief about history and origin of nanotechnology. So the first time the idea of nanotech was mentioned was in 1959 by a scientist, Richard Feynman. He made a famous quote that there is plenty of room at the bottom. What he meant by that was there is plenty of potential, or there is plenty of usage at nano level, or there is plenty of applications at nano level. What he meant by room was applications, and what he meant by bottom was nano scale or nano level. In 1974, a Japanese scientist, Norio Taniguchi, coined the term nanotechnology. So nanotechnology term was first coined in 1974. The first major milestone in the field of nanotechnology came about in 1981 with the invention of scanning tunneling microscope. It had such a fine resolution that it could see an individual atom. So for the first time, humanity could see at the size or at the resolution of an individual atom. It could finally see for the first time at the scale of nano level. And another next major milestone that came was the accidental discovery of fullerences or buckyballs. These are carbon-based nanomaterials. So this is a brief history and origin of nanomaterials. Let us now talk about nanomaterials and their types. So when we talk about nanomaterials, we define nanomaterials as any substance with at least one external dimension smaller than 100 nanometer. Any material has three dimensions: length, breadth of height or height. If at least any one of them, is smaller than 100 nanometers, we say that that particular material is a nanomaterial. Now, when we discuss types, we can classify nanomaterials on two bases: on the basis of origin and on the basis of dimensions. On the basis of dimensions, nanomaterials can be 2D, 1D, or 0D. On the basis of origin, nanomaterials can be natural or artificial or man-made. Further, artificial nanomaterials can be classified as carbon-based nanomaterials or metallic nanomaterials. Let's start with nanomaterial types based on dimensions. Now we have already discussed that there are three types of nanomaterials based on dimensions. The first is 2D type nanomaterial. If exactly one dimension of a material, of a nanomaterial is smaller than 100 nanometer, it is a 2D type nanomaterial. Just imagine this. If one dimension of a material is smaller than 100 nanometer, suppose this is the nanomaterial. Two of its dimension, its length and its breadth, they can be bigger than 100 nanometer. They can be even in macro scale. Whereas one of its dimensions, say its width, it has to be smaller than 100 nanometers. So it has to be smaller than, the width is smaller than 100 nanometers. So this particular nanomaterial, 2D type nanomaterial, it will look like a sheet. It will look like a sheet. It will look like a sheet like here. So this is also known as nanosheets or nanomembranes, nanofilms, nanolayers. That is why 2D nanomaterial is called a nanosheet. A 1D type nanomaterial has two dimensions smaller than 100 nanometer. It has two dimensions smaller than 100 nanometers. Suppose this is a 1D type nanomaterial. Its one dimension is bigger than 100 nanometer, whereas its other two dimensions are smaller than 100 nanometer. So it will look like a wire like these. So it is also called a nanowire or nanofiber, nanobars, nanotubes, nanoribbons. These are 1D type nanomaterials. And the last is 0D type nanomaterial. If all the three dimensions are smaller than 100 nanometer, it is a 0D type nanomaterial. If all the three dimensions are smaller than 100 nanometer, then the nanomaterial will look like a dot, right? That is why these are also called as quantum dots or nanoparticles. These are some of the terms used for these particular nanomaterials. So we have covered types based on dimensions. Let us now discuss nanomaterials types based on origin. Based on origin, nanomaterials can be natural or artificial. Let us start with natural type of nanomaterials. Natural nanomaterials are the ones which have no type of human involvement. So without any human involvement. To understand natural type of nanomaterials, we must understand some phenomena that occurs in nature. The first such phenomena is iridescence or structural coloration. Structural coloration is basically when there is a change in color with the change in angle of light. When there is a change in color with the change in angle of light. Let us understand this with some examples. First example is a pigeon's neck. If you have seen a pigeon's neck, you must have seen that it has a shine to it. It has some colorful shine to it. when the pigeon moves its neck, the shine and the color, it also changes. What happens is there are some nano crystals of wax in the pigeon's neck. When light falls on them, there is a color to it. When the light angle changes, when the pigeon moves its neck or the angle of light changes, because of these nanocrystals, the color also changes. Another such examples of structural coloration is a peacock's feather or butterfly's wings. These are all examples of structural coloration, and these are all because of nanocrystals of wax. This phenomena is used in currency notes. If you have seen the currency notes, you must have seen that when we flip the currency notes, when we twist them and turn them, some information comes out of them. Some images can appear, disappear. Some logos can appear, disappear. Some numbers can appear, disappear. There is also a strip on the currency note that sometimes shine. That is because of structural coloration. This phenomenon is also used in car paints. If you look at cars at certain angles, they give a certain shine. That is because of iridescence. It is also used in some textiles, some fabrics. Another phenomena is fluorescence. What happens in fluorescence? There is a fast or quick transition of electrons from the ground state excited due to absorbed radiation. So we have an electron at ground state or at stable state. Some radiation falls on it and the electron absorbs this radiation. Due to absorption of this radiation, the electron jumps to a higher state or an excited state. After jumping, it comes directly back to its stable state. So the electron is at its stable state. It jumps to a higher state due to some absorbed radiation, and it directly comes back to its stable state. When coming back to its stable state, it re-emits this absorbed radiation in the form of some visible light. So as a result of this process, some visible light is emitted. This phenomena is observed in some species of jellyfish. When these jellyfish are exposed to some radiation, they emit a green color. This phenomena is also observed in some diatoms on beaches. When they are exposed to some radiation, they observe a blue color. They emit a blue color. This is because of the phenomena called fluorescence. This is fast or quick because the electron jumps directly to the excited state and comes directly back to its stable state. Another such similar phenomena is phosphorescence. Phosphorescence is very similar to fluorescence as in how it behaves. The only difference is while the electron coming back to its ground state from the excited state, it does not come back directly, but it comes back indirectly. So the electron comes back to the ground state indirectly, along with emission of some visible light. Because the electron comes back indirectly, because there is a delay, that light emission is for a longer period of time. Because it comes back indirectly, the transition of electrons is delayed. And this light emission is for a much longer time compared to fluorescence. This phenomena is observed in watch dials, in glow-in-the-dark stickers, on road strips in the dark. These are all examples of phosphorescence. Another such phenomena that we talk about is bioluminescence or chemiluminescence. When light is produced by a chemical reaction within a living organism, it is called bioluminescence. Light is produced as a result of a chemical reaction within a living organism. So the chemical reaction is taking place within a living organism. This process is called bioluminescence. Suppose this is our chemical reaction. Some substances A and B chemically react to produce C and some energy. This produced energy is emitted as light, and this is called luminescence. This is known as luminescence. When this chemical reaction is taking place inside a living organism, inside a biological entity, this is called bioluminescence. In this process, no heat is involved. So it is also called as cold light. It is also called as cold light. It is observed in fireflies. In fireflies, firefly is a living organism. Some chemical reactions happen inside the firefly due to which some light is emitted. It is observed in some species of fungi. Some light is emitted due to some chemical reaction. Another phenomena we talk about is lotus effect. The leaves of lotus, they are hydrophobic in nature. They are hydrophobic in nature. They are scared of water. If we magnify the leaves of water, they look of lotus, they look like this. On the surface, there are nanocrystals of wax. These pointy little structures, they are nanocrystals of wax. And they are hydrophobic in nature. They are scared of water. So what happens is, whenever water falls on these leaves, they try to minimize the contact between water and surface. For that to happen, what they do is they convert these water droplets into spherical shape. By converting them into spherical shape, the contact between water and surface is minimized. This is called as lotus effect. This effect is used in making water repellent paints, in water repellent textiles. So we have talked about natural nanomaterials. Next is artificial nanomaterials or man-made nanomaterials. There are two types of artificial nanomaterials. One is carbon-based. Carbon-based nanomaterials are also called graphene. We can obtain nanosheets from it, nanotubes from it, fullerences from it. All these are obtained from graphene. Because of that reason, graphene is also called as mother of all graphitic nanostructures. And it is very important in our discussion. In our topic of nanotechnology, graphene is very important. It is called as mother of all graphitic nanostructures. Let us now discuss graphene. If we look at graphene, then graphene is nothing but a monolayer sheet of carbon atoms. This is a structure of graphene. Its length and breadth can be more than 100 nanometers. Graphene is a 2D nanomaterial. So two of its dimensions are more than 100 nanometers. Its length and breadth can be more than 100 nanometers. But its width consists of only one carbon atom. It is only one carbon atom thick. And these carbon atoms are linked together in a hexagonal pattern. This is a structure of graphene. All the carbon atoms are linked together in a hexagonal pattern. Each carbon atom forms two single bonds and one double bond. Two single bonds and one double bond. This is a structure of graphene. This figure A is graphene. Now, if we stack multiple layers of graphene one over another, this is a layer of graphene. This is a layer of graphene. This is a layer of graphene. If we stack multiple layers of graphene one over another, we obtain graphite. So graphite is nothing but a multi-layer sheet of carbon atoms. Graphene is a monolayer sheet of carbon atoms. Graphene is a multi-layer sheet of carbon atoms. And within this multi-layer sheet, corresponding carbon atoms of different sheets, they are linked together. They are bonded together by van der Waals forces. By van der Waals force. This van der Waals force is weak in nature. By nature, it is weak. Because of that, graphite is soft and it is very easy to break. So from graphite, we can obtain graphene. And if we stack multiple layers of graphene together, we obtain graphite. properties of graphene. Graphene is very, very important, and because of its properties, let us discuss them. Graphene is among the thinnest nanomaterial or among the thinnest material we have created so far. As you know, it is only one carbon atom thick. Diameter of a carbon atom is about 0.14 nanometer. So graphene is only about 0.14 nanometer thin. So it is the thinnest nanomaterial or the thinnest material we have ever produced so far. It is also one of the strongest material. It is 300 times stronger than steel. It is very good thermal and electrical conductor. It is transparent in nature. It has a very high surface area to volume ratio because it is a nanomaterial. It is impermeable in nature. It does not allow any liquids to pass through it. It is also very elastic. Because of such diverse properties, graphene becomes very important. Applications of graphene. Graphene can be used in display technology because it is thin, because it is transparent, because it is strong, because it is flexible. It can be used in display technology. It can be used in solar cells. It is transparent. It is thin. It is strong. It is very good conductor of heat and electricity. It can be used in bionics. It can be used in making aircrafts because it is strong, because it is flexible. It can be used in energy storage devices because it is a very good electrical and heat conductor. It can be used in water filters because it is impermeable. It can be used in heavy construction. So graphene finds numerous applications in numerous sectors. Now we talk about carbon nanotubes. We already discussed that if we roll graphene into a tube, we obtain carbon nanotube. Suppose this is graphene. This is a sheet of graphene. If we simply roll it into a tube like this, we obtain a carbon nanotube. If we only have one single tube, we call it a single-walled carbon nanotube. If there is only a single wall of carbon atoms, we call it a single-walled carbon nanotube. If we place multiple such carbon nanotubes, one into another, concentrically, we obtain a multi-walled carbon nanotubes. Basically, there are multiple single-walled carbon nanotubes inside each other to obtain. So we obtain a multi-walled carbon nanotube. It was developed by Sumio Lijima in 1991. It is nothing but graphene rolled into tubes. It is a 1D nanomaterial, and its properties are similar to graphene. It can be used in making computer chips. These computer chips are faster, more efficient, more effective than conventional computer chips. It can be used in transmission line cables. It can be used in making armored vehicles because it is strong, because it is thin, because it is flexible. It can be used in making stain and water repellent textiles. It has many uses in biomedical field. It can be used to make prosthetics because it is flexible, because it is strong. It can be used in making stents because it is small and strong. It can be used for DNA insertion. Basically, it can be used in genetic engineering. DNA can be used, carbon nanotubes can be used to transport DNA. Fullerences. If we convert graphene into a spherical form, we obtain fullerences. It was accidentally discovered by Buckminster Fuller. That from his name came the name fullerene. That is why it is also called as buckyball or Buckminster fullerene or simply fullerences. If we talk about structure of a fullerene, then the minimum number of carbon atoms that we require to make a fullerene is 18. So the smallest fullerene that can be obtained is made of 18 carbon atoms, and the largest can be of hundreds of carbon atoms. There is no large limit on the largest side. But the problem is that all these are very hard to make, and all of them are very unstable. They are not stable. They break immediately as soon as they are made, except one, except C60. C60 is basically a fullerene made of 60 carbon atoms. Except C60, all of the fullerenes are highly unstable. Whereas C60 is highly stable and very easy to make. So whenever we talk about fullerene, we by default talk about C60 or a fullerene made of 60 carbon atoms. If we look at this image, it is an image of C60. There are 12 pentagons and 20 hexagons in a C60 fullerene. We have 12 pentagons and 20 hexagons. Every hexagon is surrounded by 3 hexagons and 3 pentagons. Whereas every pentagon is surrounded by 5 hexagons. So no two pentagons are adjacent in the structure of C60. Its properties are also same as properties of graphene. It can be used in solar cells. It can be used as a hydrogen storage device in fuel cells. It can be converted to diamonds at suitable temperature and pressure. Nowadays, there are many issues with natural diamonds, with diamonds that are mined out of diamond mines. There are a lot of child labor issues, a lot of labor issues. So generally, the diamonds we find nowadays in the market, they're not natural diamonds, they're artificial diamonds. They're made in labs. And that is how they're made. Fullerenes are used to make these diamonds. At suitable temperature and pressure, they can be converted to goods. It can be used as targeted drug delivery. What happens is fullerenes are used as nanocapsules. They contain the drug, the medicine. They are ingested in the body, and that capsule, it goes itself to the intended target and deliver the drug, deliver the medicine. So instead of ingesting the medicine orally, instead of the medicine reacting on the entire body, only the diseased part or only the interested part is acted upon by the drug. This helps us avoid any side effects. Fullerenes can also be used as antimicrobial agents. Metal-based nanomaterials. In this, we discuss some examples. The first is gold. Gold nanomaterials can be used as magic bullets. It is similar to fullerenes. Gold nanomaterials, they can be used as a nanocapsule. Some DNA is inserted in them. Then this nanocapsule, it goes to the intended target, and at that target, it can be used to modify the DNA. So it is used in genetic experimentation. It is also used as nano cage. This nano cage, it consists of some medicine, consists of some drug, which can be used as for targeted drug delivery. Another example of metal-based nanomaterial is silver. It has antimicrobial nature. We have already discussed silver to some extent. It is antibacterial. It can be used to make anti-odor clothes. So the clothes made of silver using silver nanomaterials will not have any foul odor. Only the clothes won't have some foul odor. The body still might. It can be used for healing wounds. Vanadium and tungsten. Vanadium and tungsten nanomaterials can be used to add hardness in materials. They can be used in optical lenses. They can be used as catalysts and enzymes. Oxides of zinc and titanium. We have already read that zinc oxide nanomaterial can be used for sunscreen. They can also be used to manufacture self-cleaning glass. What happens is, on the layer on glass, a coat of zinc oxide and titanium oxide is deposited. This layer, it is hydrophilic in nature. It is water loving in nature. So it absorbs water from the atmosphere. This absorbed water, it collects on the layer of glass. The dirt that is present on the glass, it gets dissolved in the water, and because of gravity, this water then comes down. So the glass cleans itself. It has a clean, self-cleaning property. Some other sector-specific applications. We have already discussed a lot of applications of nanomaterials, a lot of sector specific applications also. We discuss some other sector specific applications here. Nanomaterials can also be used in agriculture. For example, nanocapsules to deliver pesticides. It is similar to using nanocapsules to deliver drugs, targeted drug delivery. Basically any kind of targeted delivery, whether it is delivery of medicines, pesticides, DNA and genetic experimentation, nanomaterials can be used. Similarly, controlled delivery of growth hormones. This is also a type of targeted drug delivery. Nanosensors to monitor soil health. Targeted genetic engineering, genetically modified crops. Space sector. It can be used to make lightweight and stronger spaceships due to carbon nanotubes. Carbon nanotubes can be used to make spaceships that are lightweight and stronger. Nanosensors to monitor chemicals and run experiments in space. Nanocapsules for nutrients and drug deliveries. Electronics, nanorams, nano batteries, nano generators. If you are talking about nano devices, we need power sources that are also of nano size. So we can use nano batteries. Instead of using batteries, we can use power generating source, a nano generator directly, instead of using batteries. So these are some examples of sector specific applications. The last thing we talk about in this video is issues with nanotechnology. While discussing issues, we have some terms to discuss. The first is nanotoxicology. Nanotoxicology is the study of potential health risks of nanomaterials. There are some potential health risks of nanomaterials that are involved. Another term is nanopollution. It is a term used to describe waste generated by nano devices and nanomaterials. Obviously, we are talking about using nanomaterials. We are talking about manufacturing nanomaterials. So there must also be some waste that would be generated when these nanomaterials are discarded. There would be some waste that is generated when these nanomaterials are no longer of use. They will be waste. How to handle them? So whatever pollution that is generated because of these nanomaterials, it is called as nano pollution. Already we are dealing with microplastics, pollution at micro level. So the next type of pollution that we will be talking about in future will be nano pollution. We will be talking about nanoplastics. We will be talking about pollution at nano level. So nano pollution is a real issue with nanotechnology. So the first issue is environmental pollution. Again, nano pollution. We are talking about microplastics. Micro pollution is a major concern presently. But in future, if we go towards or if we move towards nanotechnology, we will have a new type of pollution, nano pollution at hand, which we have to deal with. Another issue is security issue. You must have seen in a lot of science fiction movies how scientists or researchers they make these drones that look like common houseflies. They use them to attack someone, or they use them to record sensitive data, right? So theoretically, nano devices can be made, drones can be made, some other kind of device can be made on nano scale, which can be used to deliver some, say, poison to some particular person, which can be used for assassination, which can be used to record some sensitive information, some national security information. So there is a real security issue with nanotechnology. Another issue is equity. To research nanotechnology, you need a lot of money, you need a lot of manpower, you need a lot of know-how. Not every country can afford that. Some countries can afford it better. Western countries can afford it much better than us. We can afford it much better than maybe, say, some African countries. So there is a question on equity. It is not equitably distributed, right? So we have a genuine concern of equity. Another question that arises is whether it is ethical. We have discussed that nanotechnology can be used for genetic experimentation. It can be used to deliver some DNA, some growth hormones. So theoretically, in the future, it is possible that nanotechnology can be used to modify humans. It can be used to give them some certain desirable characteristics. It can be used to make them stronger, to make them healthier, to make them taller. Whether it is ethical, the question then arises if it is ethical to build better humans, to genetically modify humans. So a ethical question certainly. Another issue is with the blood brain barrier. This barrier is, there is a network of vessels, blood vessels and tissues which acts as a barrier to our brain. It helps keep harmful substances from reaching our brain. Now, what happens is nanomaterials or materials of nano size, it can surpass this barrier. So, nanomaterials can reach our brain and it can affect our brain in a negative manner. So, due to nano pollution, if tomorrow nano pollution increases, then nanomaterials, harmful nanomaterials will also increase. They will also be, their quantity will also increase in the atmosphere. If they reach us, if they reach near our brain, the blood brain barrier cannot help stop them. So they can harm our brain in many ways. They can they can have a negative effect on our brain. There can be mental issues, emotional issues, even physical issues with our brain because of nanomaterials reacting with our brain in a negative manner. So these are all the issues that must be addressed or that must be kept in mind while dealing with nanotechnology. So with that, we come to an end to our video.